Hello and thank you for attending my talk. I am Hoàng Hải Nguyễn. I am a PhD student in Laboratory for System Theory and Control of Professor Rob Van Eisen. I would like to present the collaborative work of my group, including Professor Van Eisen, Tim Zicker, and me, and the group of Professor Richard Bratz with Sandra Wells and Anastasia Nicolaou-Paulo from MIT. The title of the paper is Stability Certificates for Neural Network Learning-Based Controllers Using Robust Control Theory. In practice, we have many systems that are operated by a baseline controller that can deliver a good closed-loop performance, and the nominal model of the plant can be obtained, but mathematical description of the baseline controller is unknown. An example might be a human operating a car where the dynamics of the car can be modeled sufficiently well, but a mathematical model of the human control actions is not available. Or it can happen when baseline controllers are only available in hardware as they have been designed a long time ago or by a different person, and we want to imitate the behavior of such a controller to implement on a new hardware or to expand its range of operation. Or another case is the existing baseline controller may be computationally expensive, for example MPC, which prevents us from using it in very fast or low-cost systems. In those scenarios, how can we improve performance and automate the process? And often in these cases, no stability guarantees are available. So the idea is we may want to approximate the baseline controller by a trained static neural network to imitate the baseline controller. For example, the human operator, as I mentioned before, to decrease the computational load of the controller, and we can combine data with simulation. So the first question is, can we verify performance and safety guarantees for nominal system with neural network learning-based controller? Second, what is the sensitivity and robustness of the system when it operates under disturbance? And last but not least, can guarantees be embedded in the training? There are several works that look into this direction and solve the problem for learning a specific type of controller or specific type of neural network. Can we have a framework to solve the problem? So we propose a different approach by using the tools from robust control theory. We can use the fact that the most commonly used nonlinear activation functions for neural networks are sector-bounded, or can be transformed to be sector-bounded by using loop transformation techniques. And the slopes of those functions are also bounded. Basically, we reformulate the closed-loop system in form of a diagonal nonlinear differential inclusion or Luray differential inclusion, which means we decompose the closed loop into static nonlinearity and dynamic system, and use robust control stability results for controller verification. The approach is motivated by the framework of Kim and others in 2018, which considers the stability analysis of open-loop dynamic artificial neural networks, where the neural network has one hidden layer only. Here we have extended the result to the case that the network can have more than one hidden layers, which includes the case of deep neural network, and applied it to verify the stability of the closed-loop system. The system to be controlled is linear, and assume that the metric AS and BS are known. The system is stabilizable and all states are observable. Assume that we have a baseline state feedback that achieves desired closed-loop properties, and then we can obtain the data set from this baseline controller to train the network that acts as the learning-based controller. By doing this, we don't need a mathematical description of the baseline controller, and we also don't require that the baseline controller has to provide theoretical guarantees, such as nominal closed-loop stability. For example, in the case of the human driving the cars we mentioned previously, we want to imitate the behaviors, but the driver cannot provide any provable stability of the system from a theoretical perspective. But by using our approach, we can still verify the stability of the closed-loop system while imitating the behaviors. The stability of system with sector-bounded nonlinearities has been investigated since the 1940s. Such systems can be represented in the standard nonlinear operator form. So the SNOF is an interconnection of a linear time invariant dynamic system in feedback with the bounded memories nonlinearity, and it can be presented as in the figure. Many sufficient stability conditions with various degrees of conservatism exist. So by taking into account the bottom slope of the nonlinearity function, Kim and the others in 2018 derived a sufficient stability conditions that were less conservative than others' methods. The basic idea is that in the Lyapunov function, the third term was added that reflects the bottom slope of the nonlinearity, and in this paper, they conducted several benchmarks to compare the results with other approaches, and it shows that the results obtain the least conservatism. So now the questions are, can this be used for neural network-based controllers in a reasonable way? And are neural networks slope sector-bounded? So we can talk about the sector-bounded and slope-restricted nonlinearity. If we define the sector-bounded phi as being the region from 0 to c, it means that it includes all the functions that lie in the region between the x-axis and the linear function that had a slope c, which means the gray area in this figure. And if we define the function is slope restricted in the region from 0 to mu, it means that the slope of the function is always in the range from 0 to mu. With these definitions, we can see that the ReLU and the Tang hyperbolic function are both sector-bounded and slope-bounded in the region from 0 to 1. But the sigmoid function is only slope-bounded, as you can see in the figure. However, there is a technique in nonlinear control called loop transformation that can transform this function into the sector-bounded function. So first, we need to reformulate our problem into the SNOF form and then can apply the result for SNOF. The main idea here is that because the neural network contains both linear and nonlinear function inside, we will use some auxiliary variables such that we can pull out the nonlinear function and separate all the nonlinearity in one part and the other part only contains linear terms. Okay, so this is the equation describing the neural network variables. So we can use the variables qi and pi here, and we can write the dynamics of the closed loop system in a big block like this. If we compare it to the SNOF form, we can see that the matrix AS is corresponding to the matrix A, the block in yellow is B, the red block is C, and the green block here is matrix D. And this is the main result of the paper. And the matrix G is shown here, although it may look complicated, but actually it is simple to check with many available solvers for SDP problem. From this result, we can extend it to compute a convergence rate by formulating it as a generalized eigenvalue problem. The second case is when the nonlinear activation function is an odd function, for example, hyperbolic tangent. We can have a less conservatism result. The details can be found in the paper. Now we consider the case when the system is under disturbance. Omega here is a bounded disturbance that affects the system. The L2 gain of the closed loop system is defined as the supremum ratio between output and input. Basically, L2 gain of an input-output system describes the maximum gain in energy transmission from input to output. So the upper bound gamma of this gain can be obtained by solving the optimization problem, in which the metric H here is like an extended version of the metric G before, and the details can be found in the paper. So this result allows us to analyze the robustness of the closed loop system. We can replace the L2 gain with the root mean square gain and obtain similar results. So this condition can be applied for both decaying and persistent disturbance. We have implemented an illustrative example in which the plant is the interior permanent magnet synchronous machine. The disturbances are summarized in D, for example, the flux change. The baseline controller here is an MPC. So we want to illustrate this scenario. The MPC performs well without theoretically provable stability, and we want to imitate this controller and verify the stability of the learning-based controller. The neural network we use here has 5 hidden layers, and each hidden layer has 5 nodes. We do the simulation with the neural network-based controller. Several control and state trajectories with different initial conditions have been plotted, and it shows that the convergence and they perform similar to the MPC controller. the stability of the closed-loop system is only proved by using our results. So, in conclusion, we have used robust control theory to derive sufficient conditions for the certification of nominal stability of a system controlled by a neural network-based controller. So we use the sector boundedness and the slope restrictions, and the baseline controller does not need to be available in mathematical form. It can be efficiently evaluated using standard solvers. We also can derive L2 gain performance bounds, which help us to analyze the closed-loop sensitivity and robustness. The outline results and ideas are only the first steps for a more general framework. This approach can be extended to a class of nonlinear systems where the nonlinear functions satisfy Lipschitz continuity, and different types of neural networks such as recurrent neural network or residual neural network. We can extend to output feedback control case. And finally, the stability conditions can be enforced during the training process for the neural network. So this is the end of my talk. Thank you for listening, and I'm glad to answer all the questions that you may have.